Swayam Prabha. Digital India. Educated India.
Okay. So the algorithm proceeds in several stages. Okay. Because our agenda, remember, is to solve this question in this much amount of time, I can actually take exponential 2 to the power k log k time to actually this is the time. So as far as k, remember, is the number of upsets, right? So if I knew the number of upset games, I can essentially use exponential amount of time to figure out the relationship between those vertices. If I knew the set of players who are participating in those upset games, then this time complexity basically tells me, it's like a clue that, okay, then I can use exponential amount of time to figure out the relationship between those players in this SBA, if such an exists, right? That's what I'm going to do. So first step would be to guess something. By guess, what I mean is basically I will try all possible things, all possible ways of doing something, and I'll explain what this formally means. And if there exists an SBA in which my favorite is the root, then as I enumerate those structures, then one of those guesses will basically be consistent with that hypothetical solution. That's what I mean by a guess. So I enumerate a bunch of things, and one of those things will basically lead to my solution. Second step would be to verify. Let's just go back a little. To verify. So as we saw before, this is why I explained those properties before. If I just try all possible guesses, it cannot possibly lead to an SBA, because SBA has a lot of very structured properties, sizes, path lengths, and this and that. So basically, when I'm guessing these things, for each of those guesses, I should basically verify whether those guesses, because I'm doing independent, I'm guessing things independently, I'm trying all possible things, so I should basically check whether all those guesses can work together to actually generate an SBA. So that's this verify step, okay? So most of the guesses will be ruled to be infeasible, like they cannot possibly be part of an SBA, so we basically get rid of them. So this is a cleaning up step, okay? And the third step, so all those guesses, like the ones that we get in the first step, which go through the second step, will move on to the third step. So here, basically, we will use a greedy strategy to fill out the information that is missing from step 1 and step 2. Okay? So here, because of this guesswork, here we'll take exponential amount of time to exponential. Always remember, this is the target. So I can take feasibly this much amount of time in the first step itself, as long as I don't exceed this much in step 2 and step 3. Okay? So that's how we will proceed. Okay. So what do we guess? Basically, what we guess is the relationship, roughly speaking, between those players which are part of that upset games. So this is what I call the template of that. So imagine that there exists an SBA, there exists a tree rooted in the favorite, a directed downward tree, and I'm basically trying to find that tree. Okay? There exists such a thing, I don't know what it looks like, and so on and so forth. I know the set of players that will participate if they play against each other, that there will be upset games, like the lower ranked team will beat the higher ranked team. Okay? So using that information, I basically guess the partial structure of that SBA, where the certain paths will be compressed, so it's like a those edges and add vertices to it, and then it will resemble the actual SBA. Okay? So that's what this is. So I guess a compressed tree. The second information that I guess is the relation. So do you know what is least common ancestor is in a tree of 2 vertices? In a rooted tree, do you know what a least common ancestor is? Okay, so we'll go. So let's just take this for a moment, that we also guess the position of the affected vertices. So the affected vertices are the ones that are basically participating in those upset games. Okay, this is just another name. and the position of their least common ancestor. So I look at every pair of these affected vertices and see where their least common ancestor might be. I have no idea where they would be in the real actual tree, but I sort of try all possible things, and then I generate all these sort of templates by doing that. And also I guess is the length of path between these upset games. So if this is my sort of, let's call it, this is favorite, because this is the tree I'm guessing, root will always be favorite. Say this is, what was that? Okay, we'll run into an example. So this is, say, AB. This is this thing. So this is sort of the type of structure that I'm guessing. I don't know whether, I don't know yet whether in the eventual SBA that I'm trying to find, if A and B are actually playing this edge, direct edge would mean that they're actually playing each other. But I don't know whether that will be the case. I will actually guess all possible situations in which maybe A does not play against B, but there are few other teams that they play against. So meaning A plays against, say, A1, A1 plays against A2, and so on. And then eventually, as I go down this path, the last person in this path gets to play against B. Okay? So all I know is A has, this sort of structure tells me that A has proceeded to a round higher than B as well as C. So this is sort of the information I guess in the first round, in the first phase. Okay? And these length of these paths are also guessed. And there are subtrees that I suppress. So these subtrees, okay, they do not contain any upset games. These are vertices that do not participate in any upset game. They always lose to higher ranked players. These, I have no information about where these vertices exist. All I am doing is guessing how large the subtree rooted at B would be. Similarly, I also guess how large the subtree rooted at C will be, and so on. Next step is sort of this thing that all these guesses, they satisfy the SBA property and so on. And so if it does not, we basically discard that guess, and so we move on to the next step. So in the last step, that guessed structures that we did, like these were these paths that I guessed, let's say length AB, A pointing down to B. I will try to, this basically tells me that there are this many number of internal vertices. Let's say there are 5 between A and B in that hypothetical SBA, right? The one that I'm actually trying to find. So I will have to find 5 vertices which are not part of that upset games, the unaffected vertices, and add them to this. This is what I do in the third step. Similarly, the subtrees that I have suppressed underneath B that do not contain any upset games, I also fill them out, because I also know the size. I have also guessed the size of this subtree. So these are the all the missing information I fill out in the last step. Okay? All right. So how am I doing time wise? Another half an hour. Okay, that's sort of okay. Yeah, you were asking a question. Correct. So yeah. So yes. Not acyclic subtournament, an acyclic tree, subtree. Yes, yes, yes. Yes. It need not be. So yeah, so that sort of thing. So how far, so the interval around B is what these lengths tell me in a way. So what this is suppose A and B are those affected vertices, meaning these are vertices which will be part of some upset games, okay? I don't know whether I'm not saying that A and B will play against each other and therefore B will beat A, that's not what I'm saying. I'm saying A and B are part of some upset matchups, okay? So either A will beat a team which is ranked higher than it, or will get beaten by a team lower than it. The fact that in my guessed structure, this template, I have guessed that A sits above B, okay, in that SBA, and the length between A and B is 5, okay, tells me that in that, I am telling you ahead, basically this is what you can expect, that in that topological order, okay, if A sits here and B sits here, okay, then the vertices that sit between A and B, which are not part of the upset matchups, they will be used to fill up these this length. So therefore, the question she was asking, that's sort of the intuition that when you know these affected vertices, where they are placed, that sort of tells you what is the sort of the ball around them that you should look for players to fill out these things, these in between matchups, right? So that answers your question. So that's what will happen. The reason the greedy works is because those sorts of properties actually hold for this, okay? So one has to prove that those things happen, but they do, and that's the sort of the proof of correctness of this greedy strategy. Okay, yeah, oh, thanks. All right, so least common ancestor and closure of the least common ancestor. This is a very useful concept. So it's like if you understand this and like try to use it in some other place where you find it useful, okay. So here is a tree, okay. This is an SBA, okay. So, okay, not SBA, say it's a rooted tree, right. This is the root and all these edge arcs are pointing downwards and so on, okay. So the set X, can you see the colors? Oh no, I don't think, can you see the green? These are colored green, okay. Is it clear that some vertices are colored green, others are black? So these are the X vertices, okay. So among these two vertices, if I say who is the least common ancestor of these two vertices in this tree, would you know who that would be? This vertex. So an ancestor is a vertex that appeared in the path from the root to me. So I look at this vertex and I look at the path from the root all the way down to this. So that is this path, right? Can you see? Yes, I think this works as a this sort of a pointer. Okay, so in this path, each of these vertices are sort of its ancestors, right? So now if I look at the same sort of a path from the root to this vertex, this is the path I have. So these people are also the same. This guy and this guy share all the ancestors, like they have the exact same ancestors, right? So the least common ancestor is the ancestor that is closest to them in terms of the level. So in this case, this is the least common ancestor. Now if I say this vertex and this vertex, who would be the least common ancestor? This one and this one, can you tell? Who would be the least common ancestor of this guy and this guy? There are no labels here, but you can point something. Parent of this guy? So this one? Yes, exactly. So if I again look at the path from the root to this guy and root to this guy, this is the common portion of the path ends here. So this is the least common. Least meaning the person who is immediately above us, who is both of our ancestor. That's the notion, okay. Least common, there's a common ancestor and the who is closest to us. Okay, so doing this, so I'm going to find the least common ancestor and I'm going to define a closure set for this, okay. So I basically copied the same thing here, and so pair of vertices by vertices, we'll just run through this. So between these two vertices, this is its least common ancestor. Now, next step, now this set is part of my X prime, okay. So this vertex was not originally in X, but the moment I find the common ancestor, I add it to my set X, okay. So I'm growing the set X. So this is a common ancestor which was not originally in X, and I add this to X. So now between this vertex and this vertex, who is the common ancestor? This is the least common ancestor. This is also not part of the original set X. So I add this to x as well, okay. So that's what I mean. So now next is what happened, yeah. So now notice between this guy, between this vertex, so I'm still in the subtree, let's imagine. So between this x vertex and this x vertex, their least common ancestor is this. It is already present in my x set. So I don't have to add anything, correct? And between this guy and this guy, this is the least common ancestor. So basically this is the least common ancestor of both a pair of this vertex as well as this. So I don't have to add it. So this, this part of the tree is over. Now I move on to this side. So between this guy and this guy, who is the least common ancestor? Actually the root, right? Because that's the sort of the only part. They do not have a common edge sort of in the root to the vertex path, and so this is the only ancestor they have. Now this vertex was not part of the x set, so I also add this to the x. So this larger x, okay, x union some of these additional common ancestors which were not part of the original set is known, what we call the least common ancestor closure, okay, LCA closure set. So this is the closure set, okay, all right. So we know, it can be shown quite easily that if you have a tree, rooted tree, say T, and you have a subset of vertices, okay, in M is a subset of vertices, okay, then the least, so instead of M you can say X, I don't know why I used M, then you can say that the set of the least common ancestor closure of X, the way we describe this, can only be at most twice the size of X. So this property, okay. And also any subtree you find, okay, in this graph where basically you have the tree, and if I removed all these vertices, so imagine I remove this green and the red vertices completely. So in the subtree, subgraph that I have, obviously it will be a disconnected graph. Any subtree I find, okay, and if I look at the neighbors of this vertices in the subtree that are not part of the subtree, that are outside basically, they can be at most 2 of them. Basically you can have one edge coming in to the, so this is, if this is a subtree, this is also would be a rooted subtree, right? So there will be an edge coming in, connecting to the root, and there will be one arc actually leaving, at most one other arc leaving this, this subtree. That's what basically this says, at most 2. Okay, so now you know some useful things. So now I'm going to describe that guesses, what that meant by guessing the structure of the upset vertices, the affected vertices, okay. So suppose this is an SBA. I know this is the hypothetical SBA. So my favorite here is denoted by V star, okay, because just lack of space and so on. So the yellow vertices are the affected vertices, okay. So I'll say affected vertices. And these blue vertices are the least common ancestor vertices. See, between this yellow and yellow, this is the least common ancestor, right? So between this and this is actually the ancestor of this. So between this and this guy itself is its answer. It is the ancestor of these two things. So this is trivially true. So between this guy and this guy, the least common ancestor is V2, right? So that's the thing, and we always add our favorite to the affected set, like just sort of a reason. Okay, so this is suppose the SBA that we are trying to find, that we are given, okay. So from here, what I do is, if you notice, I am going to compress all the edges, basically. So from V star, I look down, okay, and I try to find a path so that beyond that, there does not exist any yellow vertex. So did you follow what I said? Starting from V star, I look for a path and I stop where I cannot find a yellow vertex beyond that. Can you point out one such thing? See this path, V star, V2, V4, V10. Beyond this, there are no yellow vertices, right? So this, so basically, so this is the part that I compress first, okay? Okay, forget about compress, I say delete it, okay? So because beyond this, there are no yellow vertices. Similarly, here also, I can sort of delete, I'll use maybe a cross, it's easier. Okay. What about this? Well, here obviously there is a yellow vertex, and beyond this yellow vertex there are no vertices. So I basically stop here. What about this? Well, it turns out beyond this V2 guy there are no yellow vertices, so basically I get rid of this as well, correct? Okay, so and I do this here and V9 is gotten rid of. What about V14? Well, the same thing. Now notice, why did I not get rid of V7? In this step, after I got rid of V14, why did I not get rid of V7? Because V7 did not just lead to V14, but it goes all the way down to V17, which is a yellow vertex, right? So these are the things that if I got rid of, this is the situation that okay, not yet. So this is what I do in the first case, okay? So I just get rid of all these truncate paths basically beyond which there are no yellow vertices to be found. Now furthermore, what do I do is, I go again back to the root and I go down to a blue vertex or a yellow vertex, one of these colored vertices, okay, and I see if there are no colored vertices in between, then I can sort of compress that path also. So for example, between V1, V star and V3, this is one uncolored vertex, so this path can be compressed, okay, into one arc. So similarly, between V3 and V17, now I do this not just from the root, I do it from all the blue vertices there onwards, okay. So between V3 and V17, there are these uncolored vertices V7, V13, okay, and I sort of get, I compress this path as well. So that is why V star has a child V3 after this compression, basically V1 is gotten rid of and V3 rises up. V7 and V13 is gotten rid of, so V17 becomes now a child of V3. Okay, so that's what is happening here. Similarly, here I basically get rid of this thing, and V15 becomes a child of V3. And I do this. This is what I get. Okay. Yeah. Least square. Yes. Yes. So I should probably mark this. Can you see this? Yeah. So affected vertices are those upset vertices, okay? So I just use them as a LCA, these vertices. So X are these affected vertices, and so let's call this as X. What's going on? Okay, yeah. So this is the thing. So blue vertices are those which are not in X but are part of the LCA closure. Okay, so this is what I get after compressing all these things. Now the next step that I do is I actually remove the labels of the blue vertices. This is what I call the template of this tree. This is template what? I think I chose a different pen maybe. Yeah, this is template, okay, of X in B. Sir, so yes, see the number of vertices in T delta and T star are the same. The T star has a few labels missing, that's it. Now from the previous property, what we saw was that if I only looked at the X vertex and its LCA closure vertex, right, that bigger set is at most twice the size of X. So this is a subgraph of this. The number of vertices here can be at most 2 of X, meaning there cannot be more blue vertices than there are yellow vertices. Okay? Yeah, so it's not a subgraph. So I just mean, sorry, that's actually incorrect. It is not, okay. So the thing is, it is not a subgraph if you think of the original win-lose graph, right? Because the yellow vertices, I don't know the relationship, like I don't know what is the relationship between V star and V15. Is the arc sort of, is there a, okay, this is not a good example. Let's say for this case. So between V3 and V17, I know this arc actually exists in that graph. Why? Because V3 is not an affected vertex. So it means that this edge, if it is going down, also exists in the original graph, meaning this is not one of those those edges. So this is fair, meaning you can infer some of these things, but the information that I'm missing is I don't know, for example, how do I say this? Okay, in this. Yes. Transitivity, I can infer some of these relationships, yes, you can say that but this is not, so the fact that these edges exist means that you can infer these edges exist in this original graph, in that original win-loss graph, because the original win-loss graph is a tournament graph and it has this nice transitivity properties, for example. So anytime you have an edge, you have this relationship between the white vertices, for example, from V1 to V7, you know there exists an edge between V1 and V7. Okay, so if, for example, okay, this is the example. So between imagine there were other vertices in this path. Okay, so when I'm compressing this path, okay, when I'm sort of getting rid of this and getting this sort of situation where I'm basically V3 to V17, I know this edge does exist in the win-loss graph. So it has, I have to be a bit careful as to because there can be some back arcs and so on and so forth, but some of these edges do exist. Yes. Right, correct, but I completely got rid of all the white part. So I'm truncating between, say, V3 and V17. So this edge exists in the graph. Yes. So between V4 and V10, of course, this edge exists in the graph because this edge is between, so see this V4 and V16, right? So, okay, this is a particularly bad example in which we cannot sort of see, but imagine a situation where there were sort of edges going, there were more yellow vertices here, and I got this compressed edge by basically truncating things, so on and so forth. So, because these are yellow vertices, they could be that the relationship is opposite. I think that could happen. Okay. So what will happen is when I will add these edges, it's like V4 will never have to play V10. V4 will play somebody else and that person will play somebody else and so on and so forth. Okay, I will just think about what you asked and just answer offline. Okay, so now, okay, just to go back here. So what did I do here? This is the type of information that I'm going to be guessing. I know the affected vertices. I don't know the identity of the LCA closure vertices. I don't know these vertices. I know VF, I know my V star, okay. I don't know this, what is it? These. So the people who are part of the LCA closure but not part of the affected set. Precisely these blue vertices. I don't know the identity. They exist, but I don't know. So basically, I will be guessing this structure entirely. These blue vertices are like placeholders. When I know that who this person should be, I will be placing them. That is what happens in the third step. Okay, so this is the guess part. Furthermore, what I'm going to guess in the thing is that when I guess this structure, this is only a partial structure. This is supposed to mimic this hypothetical solution that exists. So what I'm also going to guess is the length of this arc in that actual solution. I will also guess these sorts of length. What is the actual length between, these are arcs in this template tree, but in the real solution, they are basically extended paths and so on, okay. Similarly, I will also guess maybe there are subtrees underneath this and so on. Because this is an SBA, one of them has to be a single vertex, this is and so on and so forth. So all those relationships will be verified in the second step. Okay, so I also guess the size, okay, size of V star is known to be n because that's the root. I also guess the size of the subtree rooted underneath this, size of the subtree rooted underneath this. All this information is part of my guess template. So, okay, so let's just move on. I have explained what this means. Now, the question is, this guessing means what? I'm actually enumerating all possible such templates. That's what guessing means. Now, there is a famous result by Cayley. It's a well-known thing that on n vertices, the number of rooted label subtrees you can have is n to the power n minus 2. Okay, so using that, our n here would be x, the set x, Vf, the affected set, so that is size k. So basically, we if taking x to be k, we can guess the all possible templates in this much amount of time, k to the power order k. Okay, this is just application of this formula to the fact that x is k. Okay. So this is the amount of time I'm going to have to spend in guessing the possible templates. Now, if you look at this closely, this can be written as k log k. So this is where I have already spent that exponential amount of time, this much of guesswork. Now, after I'm done with this, then I'm going to, so these are all these things that we guessed, and now I'm basically going to, so what does it mean to basically guess the length? It means that, well, I'm going to find a length function. Basically, it will take each of the arcs in that template tree and basically tell me what the, how sort of large the length of the arcs should be, like how much they need to be expanded to get the original tree. So this is basically a path. This is a function from 0 to log n. And for the subtree, you, for the tree case, you basically guess 0 to 2 to the power log n. Okay. So now, once I have guessed this thing, I basically, let's see how this thing happens, because now I'll be moving to the next step. Okay. So this is the guessed situation, this is the relationship, this is my favorite guy, a favorite player, followed by F, followed by A. This is a path whose length has been guessed to be 2. Okay. So now, basically I have to go back to the win-lose graph and find 2 vertices that can be placed in here, so that these edges, okay, have these edges, because I need a rooted tree that is always pointing downwards. So these edges actually exist in this graph. This is what is going to happen next. So this, I need to find 2 vertices to place in this path, so that I get one long path between this guy to this guy. Okay. So if I see, and similarly for this and this, let's say I have guessed the length to be 1, and this is again length 2, then I can see that, okay, this is size d and so on and so forth. Okay, this was just a running example. Then, okay, I'll just rush a little bit. So this is sort of the thing that I guess for, this is one whole a template, length and size. Okay. Now, the next step is basically to find, okay, so these are just some definitions that you don't sort of need. So suppose I find, I'm able to test that those guesses can be part of an SBA. So for example, what I mean by that is, suppose this size, okay, these are both sort of and children of this guy in the template tree, right? So they will become descendants in the eventual solution. If this size and this size cannot be, because SBA has that property of the power of 2 and so on and so forth, if those sizes don't make sense because they are part of the bigger subtree rooted at this vertex, we say this guess is invalid. Okay? So basically we look for a template that can be extended to an SBA. That's what happens in the second step. And then, so this is what the realizable step is, that the thing that we guessed can actually be extended to an SBA. This is actually a polynomial time test. Basically, you are doing a DP to see if the sizes and the values sort of match up and so on. Okay. So this one takes, so the reason I am emphasizing in all this time complexity is like to show you how I get to the 2 to the power order k log k polynomial n time. Over here, I only use polynomial amount of time, and then now comes the sort of the main meat on the bone part, where basically how do I find those internal vertices. Okay. So this is a path, this is an arc that exists in my template tree. I have guessed the size to be 2. So what I am going to do is basically, in order to resolve this path, I basically need to add these internal vertices. So how I do that is basically roughly this. Okay. So there are few details involved, but basically this is what is happening. I look at where u and v sit in that topological ordering, what is this thing is. Now u in this case will be, so who are the vertices that have a label in my template? These are the affected vertices, correct? So this is an affected vertex, this is an affected vertex. So I start with this affected vertex, I go up the tree and look for the first affected vertex I can find. So this is like the path that I am going to fill out now. Following this, I basically look for a subset of vertices, the highest ranked vertices of this much size, this many number of vertices that lie between U and V. So if I have already used some vertex, then I cannot reuse it here. Whatever available vertices I have, I pick the highest of them of this much size and basically place them in this path. Okay, so that's basically the path resolution thing. So if you look at that example, then basically this is what would happen. This is internal vertices are 2, so you will add some number of, okay, this should be actually 3. This should be 3. Okay, so yeah, so it should be ABC. Okay, so this is how I resolve this thing. Now the question is, why should this actually lead to a solution? That actually requires a proof, and I'm horribly out of time, so there is no way to explain this. But the main idea was to say that if just by knowing the structure of these affected vertices, which are the upset vertices among each other, like who is an ancestor of whom and so on, I could actually deduce the relationship or the position or the matchups of all the unaffected vertices, just by basically looking at the topological order and finding vertices to basically place in them. So that's basically the idea of the algorithm. So now obviously there is another step where basically I resolve the subtrees. I fill out vertices appropriately into the subtrees because I have also compressed the subtrees, but they also only consist of unaffected vertices and so on. So I claim to you without proof that all of this can be actually done. Okay, so have you all seen greedy algorithms before? Have you all seen? So usually the point is to show that, okay, suppose there exists an optimum algorithm and you have a greedy algorithm. So if your greedy solution differs from the optimum solution, okay, then there is something you can do to the optimum solution, like you can make some changes, okay, and then by making, it's broadly called an exchange argument, your optimum algorithm looks similar to your greedy solution without actually change in cost. So here we do not have a cost notion, we just have the notion of there exists an SBA. So this proof basically goes forward as saying, okay, this is what my greedy algorithm does, but optimum has some other way of solving this problem. A tree exists there and here. Why is it different? Suppose I make some changes to there's a way of changing the optimum solution which looks more like my greedy solution, and yet I do not destroy the structure of the tree. So we do this step by step, it's an inductive proof, and so basically that's how these sorts of things happen. That every time I can sort of make some adjustment and make the optimum solution look more like the greedy, and so therefore, in other words, saying like the greedy, if I do this n number of times, basically then the optimum looks exactly like the greedy, and then basically the greedy is a valid solution. Like the greedy algorithm would actually lead to a solution, okay? So here you don't have an opt, but there exists a solution which solves this problem because there is no cost involved here, right? Yeah, I don't know why we call it opt, but yeah, that's the thing. Okay, so this is, I was never going to sort of get to the subtree resolution thing, but I think I can stop here now and sort of ask you to maybe ask some questions if you have.